Okay, so it's a pleasure to have Marc Schiffer from Radboud University as our speaker today. Marc received his PhD from University of Heidelberg, then did a postdoc at the Perimeter Institute before starting his current postdoc in Nijmegen. He has worked on various topics, including lattice models of quantum gravity, asymptotic safety, renormalization group flows, and the interaction between matter and gravity. And today he's going to tell us about exploring asymptotically safe quantum gravity on the lattice. Floor is yours.
All right. Yeah. Thanks a lot, Yasaman and Danjo, for the invitation and for the very kind introduction. So yeah, I will be talking about exploring asymptotically safe quantum gravity. And actually, when I was preparing the slides, I also decided to put a little bit of functional stuff in just to give an impression on what we can do there. But the big part of the talk will be focusing on lattice studies. And yeah, just to emphasize, I mentioned it earlier, but just to emphasize, please interrupt me at any time when something is unclear or if you have a question. I'm happy to discuss and dive into some more details. And if I don't manage to say everything I wanted to say, it's perfectly fine. So yeah, don't be shy, please. All right. To set the stage, since I think it's not everybody is working on quantum gravity here, I just wanted to start by saying why I actually think that we need quantum gravity. And I guess I mean, we would all agree that the current theoretical understanding on the one hand is very well described by general relativity, so the motion of planets and even like galaxies can very well describe with general relativity, and even now are gaining glimpse into the strong field regime of the gravitational interaction by experiments like LIGO and also the EHT. But exactly those objects, like black holes that we now have access to, they also predict, or at least theoretical models of those predict the breakdown of general relativity itself, namely the existence of curvature singularities at the center of exactly those objects. And typically one would say that at the scale where quantum effects of space-time become important, so around the Planck scale, we need a new description, and this new description of gravity at tiny scales should somehow resolve singularities in the center of black holes, or cosmological singularities are very similar to that. So while we have very strong experimental confirmations or evidence that general relativity is a good description of gravity at some scales, we know that it can only be an effective theory, and we need something else to make it fundamental. And if we look at the second building block of nature, namely particle physics, which is formulated in terms of a standard model, with the last missing puzzle being the Higgs, it's a very similar situation where we can explain most of the things that we observe to very high accuracy, and we have many high precision confirmations of the standard model. But also there, if we go to very high energies, there are so-called lambda poles, where if we trace the scale dependence of the couplings to high and high energies, the prediction of the prediction of the standard model is that these couplings diverge, which of course is unphysical and indicates again that also the standard model is just an effective theory and needs to be somehow embedded in a more fundamental theory. And it's intriguing that the scale at which these lambda poles appear is way beyond the Planck scale, which offers the opportunity that the quantum nature of space-time might just provide a UV completion for both general relativity and the standard model. So in a sense, to killing two birds with one stone, and making providing a description of nature which holds and is fundamental up to up to tiniest distance scales. And this is why I work on, or why I think we need a theory of quantum gravity, and why I also focus on adding matter to the system of quantum gravity to use the vast experimental knowledge that we observational knowledge that we have on the meta content to constrain and construct models that actually can resolve these kinds of divergences in the meta sector. And in particular, when I talk about quantum gravity, or when I think about quantum gravity, what I think about is that I take a patch of space-time here and I zoom into that patch of space-time, and then at some point there will be small fluctuation, like quantum fluctuations of space-time appearing. And if I zoom in further, these will increase. And if I try to explain or try to describe those fluctuations with the standard perturbative treatment of quantum gravity, then at some point, when zooming further in, these would grow and I would actually lose predictivity because I would have to add more and more free parameters to explain these quantum fluctuations. And instead, what could happen that if I zoom in further, the picture actually doesn't change anymore, but the theory or the system becomes scale invariant, such that nature at microscopic scales looks like a fractal, and like this is a maybe more down-to-earth representation of what a self-similar structure would look like. And this self-similarity is just a quantum realization of scale symmetry. And this scale symmetry, as any other symmetry, imposes conditions on the system. And here it imposes conditions on the theory space. So it imposes conditions on the couplings of the theory such that those free parameters that we would have to add in a pure perturbative treatment are fixed and removed by demanding that a specific symmetry, namely scale symmetry, is realized. And in a quantum field theoretic setting or sense, asymptotic safety is a quantum realization of scale symmetry. And this symmetry, scale symmetry, is actually not so unfamiliar because asymptotic freedom, as we observe in non-abelian gauge theories, for example, for QCD of the standard model, is also a realization of scale symmetry, which, however, is more like a classical realization of scale symmetry, where the coupling just goes to zero at high energies, while in asymptotic safety, the coupling would approach a finite constant at high energies, in particular above the Planck scale. And asymptotic safety, as like this notion of quantum realization of scale symmetry, is not bound to just happen in gravitational systems. So it's just this general idea of having a so-called renormalization group fixed point, so a constant which the coupling approaches at high energies. And this can be observed in non-gravitational systems, for example, gauge-Shikawa systems, where the fixed point can actually be tuned to be perturbatively close. So it's actually there is a perturbative parameter that one has to control the value of the fixed point. And also Gauss-Neveu models and others are known examples for asymptotic safety. And here I would just apply this principle of quantum scale symmetry to gravity and therefore formulate quantum gravity as a quantum field theory of the metric. So when exploring asymptotic safety for gravity, there's typically a choice of methods that one can choose to, or that one can make to look for it. And since I mentioned that it's the fixed point or the value of the Newton coupling that we're interested in is finite and non-vanishing, these perturbative method or standard perturbative quantum field theory methods are of somewhat limited use. And hence the most prominent tools to explore these non-perturbative physics are functional methods like the functional renormalization group, and lattice methods like EDT, like Euclidean or causal dynamical triangulations. And I will just spend a couple of minutes to contrast the ideas and strengths and weaknesses of these two methods. And on the functional side, what one would do is
before you go on,
yeah.
I thought you would understand from what you said already, but it isn't clear to me what you mean by scale invariant with a Newton constant that has a dimension.
Yeah, so okay, very good. So what I mean is, so what I plot here is the scale dependence of the Newton coupling, of the dimensionless version of the Newton coupling. So I've scaled, the Newton coupling has a negative mass dimension. I have scaled that one out. So the G that I plot here is the dimensionless version of the Newton coupling. And with scale invariance, I mean is that what I mean is that the dimensionless versions of all couplings, so by explicitly scaling out all the canonical mass dimensions, that those approach a renormalization group fixed point. So they become constant, or they are constant at high energies. And this means that the dimension-full versions of the couplings are in a scaling, like in a power law scaling, according to their canonical mass dimension.
So is this going to imply conformal invariance of the theory locally?
So I think this is an intricate. It's an interesting question, and conformal symmetry is like there's an additional rotational symmetry in there, and in 2D, like in two space-time dimensions, there is a proof that scale invariance plus unitarity implies conformal symmetry, but to my knowledge, there is no such example for 4 dimensions, or no such proof for 4 dimensions. I don't think there's a counterexample or a physical counterexample, but there's also no proof that this is the case. So it could be conformally invariant, but it could also, it's unclear in this sense. So it does not necessarily imply conformal invariance.
But you are also going to be working in Euclidean dimension, I suppose.
Yes. I'm also working in Euclidean spacetimes. That is true.
But that won't rule out higher derivative gravity terms, which could be pathological in a Lorentzian signature.
Well, they also have ghost and tachyonic instabilities in Euclidean signature. That is true. So
they're less
it won't rule.
Euclidean signature. I mean, Euclidean is a statistical physics setting, so they're not really a problem, I would say, unless
well, they are not a problem, but I mean, you can, you would notice whether you have additional propagating degrees of freedom beyond those of GR, right? I mean, you see whether you have like negative norm states or like negative energy scalar degrees of freedom propagating in your system. This you would still see in Euclidean signature, like if the sign of a kinetic term has the opposite sign.
If that was wrong, yes, you would see that.
So I mean, so some of these aspects we of course also see in Euclidean signature. That is true.
If the fixed point was just c-squared gravity, then I wouldn't see it necessarily as any problematic.
That is true.
Be problematic in Lorentzian.
Yes. So maybe let me actually make a couple of. I think I will come back to that question in a little bit. I don't have a slide to it, but I have a slide on the functional renormalization group where I think these questions are more easily discussed, and I will come back to it.
Broader picture. I just wanted to get the broader picture there.
Yeah, I will come back to it in just a bit. So yeah, okay. So I would say that there's two main methods: functional methods and lattice methods. And what we do on the functional side is to extract the scale dependence of couplings and operators, and then asymptotic safety, or the asymptotically safe fixed point. Or asymptotic safety is a fixed point, a so-called fixed point, so a point in theory space where the scale derivative, so this k dk, of all dimensionless versions of the couplings vanishes. And if at least one of the fixed point values is non-vanishing, then we would call it asymptotic safety compared to asymptotic freedom. On the lattice, what we do is to extract lattice correlators and order parameters of the theory, and then asymptotic safety is a continuous phase transition in this lattice parameter space. And why a continuous phase transition is related to asymptotic safety is that at a continuous phase transition, correlation lengths diverge, and the divergent correlation length means that everything is correlated. So the only length scale, or only scale on the lattice, which is the correlation length, doesn't exist anymore. So one enters a scale invariant regime. And this is also like why lattice QCD or other lattice field theories work. In a sense, one is always looking for a continuous phase transition. So in that sense, both of these methods are suitable to explore scale invariance. And they also have like advantages compared to one another. On the functional side, I would say that one can have a semi-analytical treatment, or like mostly analytical treatment, even though sometimes we need numerical integration routines. But a big part of it is analytical, and we have analytical flow equations, which allows us to easily, also because it's a purely continuous quantum field theory setup, we can easily include matter, connect to low energy physics, and can like easily vary the matter content of the theory. On the lattice side, of course, an advantage is that it's manifestly background invariant. So one doesn't put like it's just I will go in detail later. It's just a sum over all possible like geometries. So there's no preferred background or geometry, and also it's like fully non-perturbative. There's no approximations in the like perturbativity in that sense. And one has a like very good way on estimating at least statistical errors. Of course, both methods also have their downsides and their difficulties. On the functional side, again, there's that one needs approximations on the dynamics, and I will come back to that in just a little bit. One has to choose some form of regulator, gauge fixing, and other issues. While on the lattice side, one is subject to finite size effects. One needs to extrapolate to the continuum limit, continuum infinite volume limit. One somewhat needs to guess what the relevant parameters on the lattice are, and so on. So overall, both of these methods, while they have advantages, they also have like approximations and systematic uncertainties involved. And therefore, I think it's important to use both methods in parallel in a concerted fashion to explore asymptotic safety and to extract evidence for the physical features of asymptotically safe quantum gravity. So by looking at the same system with both methods and identifying the same physical features, I think we have a much stronger confidence that whatever we find is actually of physical nature and not subject to any of these systematic uncertainties in either of the methods. So let me now briefly summarize what the idea of these functional methods is. And in that context, I will also come back to the question of higher derivative and what the theory actually will look like. So the main idea of the functional of this functional methods or the functional renormalization group is, instead of integrating out all quantum fluctuations at once, which we typically do in perturbation theory, is to include quantum fluctuations in a step-by-step fashion. And in that sense, one introduces a gamma k, so which is a scale-dependent effective action, which depends on the scale k. And it includes all quantum fluctuations down to the scale k. So k is an infrared cutoff, and all quantum fluctuations with momenta higher than k, or momentum squared higher than k squared, are included in gamma k. And then by changing k, one can test the theory at different scales, and two limits are if we send k to infinity, that means that we don't integrate out any quantum fluctuations. So what we are left with is something like the classical action. And if we send k to 0, so we integrate out all quantum fluctuations, then we are left with the standard 1pi effective action that includes all quantum fluctuations. And in that sense, gamma k is just some interpolation between these two limits. And the interpolation, or like the trajectory at intermediate k, can depend on specific choices of the technical setup, but the endpoints are independent of these choices. And these are the physically interesting ones in the end. And the way one implements this integrating, the step-by-step integrating out of modes, is that one adds a mass term into the path integral. So here's just a simple scalar field. So we have a path integral with standard Euclidean action, and we just add a field that is quadratic, a term that is quadratic in the field. And here Rk can be thought of as a scale-dependent mass. And this we typically choose it with properties such that it's positive if p squared is smaller than k squared, and then there is a positive mass term for those modes in the path integral, such that those modes are suppressed in the path integral and not integrated out. And the regulator is 0 if p squared is larger than k squared, so for the high momentum modes, such that there is no suppression for those modes, and those modes are just integrated out and therefore included in gamma k. And then the functional renormalization group provides us with a flow equation, so a differential equation that describes how gamma k changes if we lower k from k to k minus delta k. And so this, I mean, it's just an equation, but it's a differential equation, and gamma k here is, well, as I said, with scale is some ansatz for an effective action, and we can extract the beta functions of couplings by projecting on the relevant field content. Now, one issue is that gamma k in principle contains all operators that are compatible with the symmetries of a system. And for gravity, this is like diffeomorphism invariance, so it includes the Einstein-Hilbert action, but then also r squared, r mu squared, r cubed, like all possible monomials that you can think of that are diffeomorphism invariant, and these are infinitely many. So gamma k includes all of them, but since we can typically only work with a finite amount of these operators, we need to truncate. So we need to choose a subset of these operators and compute the flow of those operators, which we typically call truncation. And this choice of a truncation leads to systematic uncertainties. Now, coming back to Danjo's question, I already said there will be r squared and c squared, or I mean u squared type of operators that are included in gamma k. So one could voice the question on unitarity, and this is an important question. And yeah, I don't have a slide on this here, but I should have. I apologize for that. But so it is an important question. But the point is that exactly, it's not just r squared and c squared, but it's a full function of operators. So it's really all possible momentum dependencies that one can write down. So in a sense, the propagator is really given by r f of box r and c f of box c. So this is the propagator that one will be looking at, and then it's a question on whether these form factors f of box do feature additional zeros in the, like, as a function of the Euclidean momenta, which would indicate whether there are additional degrees of freedom. And I think there was a question in the in the chat. What does the 2 in gamma 2 mean? Yeah, very a good point. So this means the second variation of the of gamma k. So it's the second variation of gamma with respect to all fields. So it's a matrix in field space. And you can think of this equation of this gamma 2 plus r as the regularized 2-point function. And so gamma 2 plus r inverse is like a regularized propagator. And therefore, we sometimes refer to it as like a one-loop equation. So yeah, it's you take your gamma and compute the 2-point function from of it. And because we introduce this regulator here in the path integral, it also shows up here in the 2-point function. Yes. So yeah. So while all operators are included, it's really important that for questions like unitarity and so on, we really have to take all operators into account, or the full momentum dependence of 2-point functions into account, to make sure that we don't see spurious poles that are just introduced by chopping off this tower of operators. And I hope that somewhat answers your question. Donjo, but please let me know if you have follow-ups.
No, I understand the setting. I'm familiar with it. You didn't describe the problems that arise with gauge theories and ghosts and things like that, which can be. So you're presumably using a full BRST invariant formulation here.
Well, no, we do need to gauge fix, and we do have like Faraday Popov ghosts, and our like gamma k will have, or the flow equations that we extract will have some residual gauge dependencies. That is correct. And when truncating, then this gauge dependence does not completely cancel out, even for objects like critical exponents. But we use sometimes, I mean, I'm a big fan of doing that, to use gauge dependence actually as a proxy on how robust the results are. So when tests for residual gauge dependencies in critical exponents or whatever observable or physical feature one is looking at, and then can estimate whether qualitative or even quantitative features of the system do or do not depend on the choice of the gauge. But yeah, I mean, we do have to gauge fix, so it's not fully BRST invariant here. And yeah, also as you mentioned earlier, we are in a Euclidean setup here, and here the Euclidean setup is partially, or so what I described here is in a Euclidean setup, and it's and you can think about it as why it's necessary to go to Euclidean is because of this notion of integrating out momentum quantum fluctuations according to the momentum shell, because only in Euclidean p squared gives you a notion on whether it's a UV mode or an IR node. In Lorentzian, this is not necessarily the case anymore. So here, typically, we've Vic rotated to Euclidean spaces, but I want to emphasize that there are, in recent years, also Lorentzian formulations of this flow equation, actually from different directions. So this is a very active part of the community trying to like extend and generalize these methods to Lorentzian space and to Lorentzian signatures. And there are first computations also for gravity on Lorentzian signatures, and in particular one that also touches on the Lorentzian signature. Sorry, on the question of unitarity is that there's a work by Jan Pawlowski, Manuel Reichert, and collaborators, where they computed the spectral function in Lorentzian. So like in Lorentzian in Lorentzian signature. So as a full function of the full Lorentzian momentum squared, and look for for additional deltas or for evidence for additional degrees of freedom. And they find that only the standard degrees of freedom of GR are present in propagating. So from that perspective, we don't have any indications that there are unitarity violating degrees of freedom in the system. But this requires to take the full momentum dependence of these propagators into account, and this is very important here.
Okay, we can come to anything associated with it. Once you've described more details, we can come back to anything.
Right. Okay, yeah. So actually, so from here, I just wanted to give you an example on what we can actually do with this method. So if you like, if you're interested in asking more questions about the method, I think this might be a good point. But I also actually, my hope was to, or my idea was to talk a little bit more about the physics that we can, or like the physical insights that we can get. But yeah, if you have more questions about the methods,
that's more important. We can come back at the end.
Okay, all right, very good. Yeah, so and as I said, I mean, the title is more on the Lattice side, so I really just wanted to give this functional method just as like in a sense as a contrast, and also like maybe as as some context on what we can do on the functional side and what we can do on the Lattice side, and why it's maybe so currently still very, very hard to compare them in a direct way. So the example that I want to talk about is related to the U1 sector of a standard model. And here, if we look at the beta function of the abelian gauge coupling, which I call gy here, at one loop it has a positive sign, and this means that the fixed point at g = 0 is infrared attractive. But like if I trace it to higher energies, it's UV repulsive. So if I start here and like close to 0 and go to higher energies, then I will be driven away from the fixed point. And this means which one can see by solving actually this differential equation, that at some finite energy scale, there is a divergence, and this we call the Landau pole. And the only way to remove that divergence, so by pushing it to higher and higher energies, is by setting the coupling to 0 at all scales. And while this is a consistent theory in the sense that there is no divergences in there, it's a non-inflecting theory, and it's also not consistent with observations because we do observe like a photon at low energies, which interacts with matter. So this is one of the motivations why I said we need something new, and I propose that this something new might be quantum gravity. And indeed, if one adds gravitational fluctuations to the system, what happens is that gravity fluctuations introduce an additional term to the scale dependence of the abelian gauge coupling, and this term is linear in the gauge coupling, which one can understand from the diagrammatic representation of this flow equation. And this Fg has the properties that it's constant at high energy, so above the Planck scale in the fixed point regime, and it quickly goes to 0 at below the Planck scale because it's proportional to the Newton coupling, which quickly approaches 0 once quantum gravitational effects turn off. And there's actually quite like strong evidence from functional renormalization group computations that Fg is actually positive above the Planck scale. And if it's positive, it means that at small values of the gauge coupling, the linear term dominates, and it therefore turns the Gaussian fixed point into an infrared repulsive direction. So it's now or UV attractive. So it's now a relevant direction, which means that it has the same properties as the strong interaction, for example. So it becomes asymptotically free. So I'm not attracted. Like if I start from high energies, I'm not attracted by this fixed point anymore, but I'm repelled from it, which means that I can start. Maybe this picture is more adequate, which means that I can start at the coupling being close to 0 at very high energies, and then I will get pushed away from 0 to finite values down at the Planck scale. And at the Planck scale, Fg goes to 0 very quickly, such that in the end, I'm only left with the standard perturbative one loop running, or like the standard perturbative running, which means that the coupling will decrease again towards lower energies. And this means that due to the quantum gravitational fluctuations, the abelian gauge coupling actually can become asymptotically free, such that quantum gravity might provide a UV completion of the abelian gauge sector in that sense. And in addition, it gives rise to, like in this very simple model, it also gives rise to a second fixed point, which is, again, infrared attractive. And this, from there on, this is the point where the screening, where the positive and negative terms in the beta function exactly cancel. And there's one particular trajectory that emanates from this fixed point, such that if this fixed point was realized, the low energy value of the abelian gauge coupling would be actually a prediction. So one could compute it from first principles, from the underlying theory of asymptotically safe quantum gravity coupled to U1 gauge field. But I mostly want to focus on.
So if I understand correctly,
yes.
what you've taken is QED essentially,
yes,
as a theory, and said QED coupled to gravity.
Exactly.
We're suggesting that the that the pole is resolved and actually becomes a fixed point, which is this.
Exactly. So that the Landau pole is resolved, and one resolves it by changing the nature of the fixed point at coupling being 0. So if I just look at QED, the fixed point is an infrared fixed point. So whatever finite value you start out in the UV, you will always get pulled towards 0 at lower energies.
I see what you're doing. It's just it's putting in a lot of belief in the perturbative regime up
but
at very high energies.
Well, so I mean the fact that of course, I motivated the existence of a Landau pole just based on one loop perturbation theory, which of course at some point, like long before the divergence of the coupling, breaks down. But there are also non-perturbative studies on whether the Landau pole exists, both with functional methods, but also on the lattice. And I think those also indicate that even non-perturbatively, the Landau pole exists, such that also like over
the Landau pole exists. What you're really, but I'm just concerned that you are using a perturbative result for QED in the at very high energies, and then putting in just some fluctuations due to gravity as well. But or maybe this result you're quoting is coming from the functional flow equation.
So I mean, this is just the universal one loop coefficient. So this one here. But what is so let's assume that the gravity and the FG, which we compute from the functional renormalization group. So this is a non-perturbative result. And also, if we compute it with the functional renormalization group, then these higher order terms will also come out. So there will be non-perturbative effects here. But assuming that this contribution here is positive, then I can try to understand what happens around GY being 0. And this is a regime where this where this term is the dominant GY equals 0 is a perturbative is a regime where perturbation theory is very well controlled. And so I'm looking at the properties of the Gaussian fixed point. And the gravitational contributions here just change the properties of the Gaussian fixed point to be a UV fixed point instead of an IR fixed point.
Yes.
So I would say that this regime back here, here I can use this approximation very well, where one would have to question this contribution is in this regime here, where G becomes sizable in a sense. So like whether this transition actually happens in the sense like that sharp, or whether there's certainly other like higher order terms in the gauge coupling will become important here. But the fixed point structure and the question whether one can UV complete the abelian gauge field, I think this is independent of these higher loop contributions in the pure abelian gauge system.
Yeah, no, it probably is, yes.
Because as I said, so I'm just asking about the Gaussian fixed point, and also the existence of this interacting fixed point at finite values of the gauge coupling. This, of course, for this I need to know these contributions better. But just for G equals 0, for the properties of for the stability properties of the G equals 0 fixed point, I think this one loop approximation is it should be valid. All right, so I think this is one example, however, where gravity, or where the existence of, or where demanding that gravity UV completes matter puts constraints on gravity, in the sense that not all values of the Newton coupling and the cosmological constant will be such that one can start at the GY equals 0 at high energies and be connected to a value of the abelian gauge coupling that is compatible with experimental observations. And I actually want to, if one goes, I want to take another step further, just to illustrate how nice and like how nice one can use this functional methods to constrain gravity. So here I plot the region where one can induce a UV completion exactly by the sign of this FG. So where FG has a positive sign in green, in the plane spanned by G, which is related to the Newton coupling, and lambda, which is related to the cosmological constant. And these are, again, all the dimensionless version of the coupling. So it's not a problem that lambda is negative. At low energies, the cosmological constant can be connected to a positive one. So, and the left panel here is at d equals to 4, and the right one is at d equals to 6. And we see that the region where the UV completion is possible in d equals to 6 has now shifted to a significantly more non-perturbative regime, because the Newton coupling is I mean, it's very large. And if one actually overlaps with demanding that other operators also become UV complete, they impose a constraint where the theory becomes strongly coupled, where one either has new divergences or new free parameters in the meta sector, and these are these red hashed regions. And one sees that they for d equals to 4, these two regions overlap, but that there's still a large region where the abelian gauge coupling can become asymptotically free while remaining in this weak gravity regime. While in d equals to 6, this is not the case, and any region where one would UV complete the gauge coupling is within this excluded strong gravity regime, such that actually the U1 gauge sector might remain UV incomplete in d equals or larger than 6, even in the presence of quantum gravity. And this, I mean, if you would turn it around, it constrains the dimensionality of our universe. If we demand that a fundamental abelian gauge coupling exists in nature. And
well, this is are you including here?
Sorry?
What additional operators are you including?
So these are like Euler-Heisenberg kind of operators. So f to the 4 and ff tilde squared operators. These are those that give rise to this strong
operators in the
meta sector. Yes.
In the meta sector. Okay.
Yes. So this is Einstein-Hilbert gravity plus f squared plus f to the 4 kind of operators, and these f to the 4 operators they also need to be UV completed. And the UV completion of these operators is only possible in this green regime and not in the hedged red one. And this is exactly this constraint that comes in there. And so we have like two competing mechanisms here, which in the end give rise to a finite region where UV completion is possible, but no region where this is possible in d equals or larger than 6. So yeah, this was just or was supposed to be just a very short illustration on what we can do with functional methods. So let me actually now go to what I was claiming was the main part of the talk, namely asymptotic safety on the lattice. And here in particular, I'm focusing on dynamical triangulations. So the idea is that we discretize space-time in terms of triangles. So we take our smooth Euclidean sphere and discretize it in terms of triangles. And then by making these triangles smaller and smaller, we eventually want to approximate a continuum sphere again. But in the process, we integrate over quantum fluctuations of geometry by summing over different gluings of these triangles. So quite literally, we replace the path integral by a sum over triangulations weighted by the discretized Einstein-Hilbert action, the so-called Einstein-Regge action. And just, yeah, I'm not sure but maybe people are not very familiar with putting gravity on the lattice. So I wanted to give some insights on how we actually compute this discretized action and what happens. So the starting point is the continuum action, just the Einstein-Hilbert action, which has the curvature term and a volume term. And we want to discretize both. So we start with the easiest one, which is discretizing the volume term. And to discretize the volume term, we just, we already discretized space-time in terms of triangles or higher order simplices, of like 4 simplices. So the volume is just the sum over all of these discretized, like all of these building blocks. So in 2D, it would be the sum of the area of triangles. In 4D, it's the sum of the volume of these 4 simplices. So the volume term is easy to discretize. Now the question is, like, how do we measure curvature on the lattice? And for this, again, let's take our intuition from 2 dimensions. So we triangulate and we use equilateral triangulations just because it's very nice and simple and it's a choice. And like if I focus at this vertex here, I can count that there's 1, 2, 3, 4, 5, 6 triangles meeting at that vertex. And if I count the angle that is enclosed at this vertex, it's 2 pi. So the deficit angle, which is 2 pi minus the enclosed angle, is 0. So we call it a flat, so this is flat. And then obviously you can do it on, this is a nice thing about 2D. You can do it on a sheet of paper and actually try it out. So this would correspond to a flat triangulation. But now imagine that you actually take a sheet of paper and you cut out one of these triangles. And then you wanted to glue these 2 blue edges to each other. Then you would immediately see that you would have to curve your sheet of paper and you would have to introduce a positive curvature on that sheet of paper. And exactly this is, so again, by counting the number of triangles, so here we only have 5 triangles. So we don't have 2 pi, which is enclosed at this vertex, but the deficit angle is positive, and this indicates positive curvature. And we could also do the opposite and glue an additional triangle here, and then try to glue this additional triangle with that blue edge. And then we would have to introduce some kind of hyperbolicity, so some local negative curvature. So curvature on the lattice is located at in 2D at vertices and in 4D at triangles. And we can compute it by the deficit angle, so really by counting how many triangles meet at a vertex or how many simplices meet at a triangle. And then we need to, for dimensional reasons, we also need to multiply those by the volume of the individual building blocks, so by the volume of the triangles in the 2D case. So now we have a discretization of the curvature term as well. So we have our discretized Einstein-Regge action, and we can actually perform these sums exactly by some redefinitions and of the couplings. We end up with an action that is that has 2 couplings, kappa 4 and kappa 2, and multiplied by n4 and n2, which is the total number of 4 simplices and 2 simplices in the triangulation. So I always find this very surprising, that in the end, the entire gravitational action only depends on the total number of 4 simplices and 2 simplices in your triangulation. And yeah, so this is the Einstein-Regge action, which we add into our path integral. And then we perform the partition sum. So this sum, or this importance sampling sum over different triangulations via Pachner moves. So we perform moves which are related to adding or removing a vertex or an edge or exchanging 2 triangles. And these preserve the topology of the system. And it's just similar, just like in if you put an Ising model on the lattice, it's the equivalent of flipping a spin in a sense. And we explore the parameter space by performing these Pachner moves. But in this vanilla version that I explained to you here, unfortunately, in 4 dimensions, there is no physical phase. So no phase where these geometries look like de Sitter or something like this. And there's also no indications for a higher order phase transition where we could take a continuum limit. So this was like heavily explored in the 90s and then at some point abandoned. And instead people imposed or like extended these models and imposed a causal structure where you, instead of gluing all triangles together in all possible ways, you impose a foliation structure and restrict the way in which you can glue the triangles together. And I see there's a question in the chat. Does the deficit angle between being greater than 0 always imply positive curvature, or could you also glue the 2 sides making a concave surface? So the So the deficit angle being positive always implies positive curvature if we glue it in this way. If you wanted to get negative curvature, you would have to add a seventh triangle. So we would have to add another triangle to the system, and then try to like somewhere here, and then try to we would have to add 7 triangles that meet at this vertex, and then glue the remaining edges together, and then you would create a concave structure. But in this notion that I introduced as curvature, positive deficit angle implies positive curvature, and negative deficit angle implies negative curvature. And in these equilateral triangulations, we can just count the number of triangles that meet at a vertex, because all of our triangles are equilateral, so we know their angles. All right, so in CDT, instead of allowing all points of gluing, one distinguishes between space-like and time-like edges, and imposes a gluing constraint that preserves some form of foliation, which means that one only takes into account those configurations that can be Wick rotated from a Lorentzian setup. And in this, I think this is like highly successful, and one has a richer phase structure because one adds a new parameter to the system, or also because one adds a new parameter to the system. And in this higher or more rich phase diagram, there is a phase where the lattices look like a de Sitter phase, and there's also several actually second order phase transition where one could imagine to take a continuum limit. What I will focus on here is, instead of imposing this gluing constraint, I will add an additional term in the action, a so-called measure term. And my interpretation of this measure term is that it has some form of overlap with higher order curvature operators. And why I think that it has something to do with higher order curvature operators is that this O of Tj is the triangle order. So exactly the number of 4 simplices that meet at a given triangle. And this is, as I explained earlier, this is just counting, or the 2D equivalent would be counting how many triangles meet at a vertex. So this is what we started out with for our definition of Regge curvature. And by having, so if I exponentiate it and put it as a part of the action, I would have something like log of this odd triangle order. So I can imagine that this might be some specific resummation of higher order curvature operators. And indeed, from functional methods, we have strong indications that an R² type of operator is a relevant direction. So with this notion, I would also have to add it on the lattice to be able to find to find a fixed point or continuum limit. And indeed, what one finds is, like, again, one enlarges the theories of the parameter space here by adding this additional coupling beta. So this AEB line is the extension of the first order point. So it's a first order line, which separates 2 unphysical regions. But the hope is that if one follows along this line, there might be a critical endpoint, which is higher order, where one can take a continuum limit. And we have...
You are also restricting to dynamical triangulations, to causal dynamical triangulations.
No, it's Euclidean. So it's purely Euclidean. So we don't have this causality constraint that CDT does.
You're dropping that. Okay.
Yes. So it's just plain vanilla like dynamical triangulation, just with this additional term in the action.
Okay.
Yes. So the question on whether or not we will resolve, or we will find something that looks like a de Sitter sphere is still a question. But I will actually, I will rush through it. But I will hope I can show you some of the results that indicate that indeed we do find indications for a de Sitter shape of our universe. But so let me take it step by step. So the question would be that if I follow along this first order line, is there hope that there might be a continuum, like a critical endpoint where I can take the continuum limit? And what we did was to actually do that, to follow along this line and compute the relative lattice spacings of our geometries at different values of this coupling kappa 2. And what we find indeed is that to going to larger kappa 2 along this line, the relative lattice spacing decreases. So
what do you mean the relative lattice spacing?
So the lattice spacing here is it's a dynamic, and it's not an input parameter. The lattice, like we discretize it in triangles, but the edge length actually completely drops out, and it's not an external input that we can dial. So every different point in theories or in this parameter space will have a dynamically determined lattice spacing.
So what do you mean by that is really what I mean, I can see that your lattice spacing has gone into your kappa 4 and kappa 2.
Mm-hmm.
It's all disappeared in there, but you must have some observable that you're tracking to determine what you want to consider as a physical length, and now you've got a lattice spacing that's presumably determined relative to that. But what is the thing that you're relativizing it with?
So what we are relativizing it, and I will show an example on how we do that. So what we do is that we perform a saddle point approximation on the lattice, which we then relate to the continuum computation, where we can relate this to the Newton, or where the Newton coupling shows up in the continuum computation. So we have an approximation which allows us to map our lattice numbers into something related to the Newton coupling. So the Newton coupling sets the physical length scale of a system, and therefore, like this allows us to extract absolute but also relative lattice spacings in that sense. But I will come to that in just a bit, or hopefully I will be able to explain it a little bit better. So this is a result. This is not an input. It's a result that the relative lattice spacing actually decreases. And what we did here was to do it like the way we determined the relative lattice spacing here was more via actually like some diffusion process. So like think about, you have a random walker, then the return probability does also depend on the size of, like, on the edge length. So by rescaling the diffusion curves of a random walker, when we were able to extract also some notion of a relative lattice spacing. But I think we have a more accurate version to do it now, which is related to like a saddle point approximation, but I will come to that in a bit. So the hope is, okay, there might be a continuum limit, but in this continuum limit, is there actually some hope that we can recover semi-classical physics, so something like a 4-dimensional space-time? And to explore this, we used matter as a probe for gravity. So we took our fluctuating random, like, triangulated geometries, and we just threw scalar fields on it, in the sense that we didn't take into account the backup, the effect of the scalar fields on the geometry, but only the effect of the geometry on the scalar fields. It's the so-called quench approximation, where we only solve the like compute the propagator or the two-point function of the scalar field. So it's very simple to discretize the action of a scalar field, where D is just the number of simplices at a given point, and A is an adjacency matrix between whether there's a link or whether X and Y are neighbors or not. So L it's the kinetic operator on the lattice, and to compute the propagator, we just have to invert that matrix. And indeed, and that's exactly what we did. And we computed the one particle propagator, so the propagator of a single particle from point X, or between 2 points at a given distance, geodesic distance r. And we know that this propagator has an exponential fall-off and a power law fall-off, and the exponential fall-off is given by the renormalized mass. And we did the same for the 2-point, the 2-particle propagator. So we took 2 particles and propagate like a 2-particle state and propagated that one. And this also has the same fall-off, but it falls off with the renormalized mass of the 2-particle bound state. And by comparing the one particle and the two particle state, we can extract the binding energy. Right? The binding energy is just the difference of 2 times the single mass minus the bound state mass. And this we can fit with some power law. So we use the fit that the binding energy is some prefactor times m to the power alpha. And in continuum in the continuum non-relativistic limit, so by solving Schrödinger's equation in a gravitational potential in 4 dimensions, one finds that this power here is actually 5. So if alpha is 5, this means that we are probing a 4-dimensional non-relativistic limit. And so this is, this is just a plot of the lattice results that we have. And I think the most important bit is that the fit and the infinite volume 0 lattice spacing extrapolation of that fit gives us that alpha is 4.6 plus minus 0.9. So it has overlap with alpha equals 5. And actually, if I performed the continuum computation, so the Schrödinger equation in gravitational potential in 3, 4, and 5 dimensions, I can kind of interpolate alpha as a function of a dimension and translate alpha into an effective dimension. And then the effective dimension that the scalar field sees when propagating on our geometries is 3.9 plus minus 0.2. So very well consistent with a 4-dimensional geometry. So I think this is a very strong indication that indeed EDT might feature a non-relativistic limit where it effectively looks like a 4-dimensional space. And this is highly non-trivial because the dimensionality that these scalar fields see it has nothing to do with the dimensionality in which these triangles are embedded. So, for example, one could be in a collapsed phase where the dimension is very high, or in a very elongated phase where the effective dimension is very low.
And how large a system can you probe there with this?
Yeah, so this is certainly a limitation that we're probing. So I think here our largest systems were of the order of a couple of I think 64,000 4 simplices. So like a couple of Planck volumes actually. So in terms of volumes, it's not. I mean, of course, the question on non-relativistic and large R and these kind of things are very subtle. So the lattices are small in that sense. But we do probe a couple of Planckian volumes.
64,000
4 simplices.
Simplices. I would have thought that would be significantly larger than a couple of Planck volumes.
Well, that depends. I mean, Planck volumes in the diameter. I mean, it's a 4-dimensional one, right? So you have to take the 4th root, and then I think it's like the radius of it is like 10-ish, like simplices. Like if you would approximate as like a perfect sphere, it would be like of a radius of 10 to 20 simplices, in that sense. And our lattice spacings are slightly below the Planck scale, so the volumes are a little bit smaller.
And how large? I mean, you had to put in a bare mass.
Yes.
For this, which presumably
we fit a range between I think 0.1 and 0.01 Planck units, so Planck masses. So it's like a Planck heavy particle.
Not only should be you want it to be probably quite a bit heavier.
Yeah, and we wanted to be heavy because if we set n to 0.
How many foldings you can get out of that to see the fall off, for instance? Reading the fall off is probably not so bad, but getting the 1/r looks difficult.
Yeah, so we actually don't fit the 1/r. Yeah. So I mean, we are only interested in the exponential here. But I agree that getting the 1/r, this is also something that I'm actually coming back to Yasaman's questions what I'm thinking about now. So this is one thing, like getting the 1/r and maybe relating that to a spectral index in cosmology. This is something we are thinking about at the moment with collaborators here in Nijmegen for CDT. But again, I mean, you need some mass, you need some finite mass to actually be able to do this inversion of the operator L. But as soon as you have a mass, you will mostly be dominated by this exponential fall off. So it's very hard to get this power law out. But I mean, yeah, we are still hopeful that we can also get statistically significant results on the power law. But here we are only interested in the exponential fall off, because this gives us the mass and the binding energy, and we were happy with that at this stage. But yeah, that's a very good observation. There's more information here, and we are looking into it. Yes. All right. So I think yeah, so we do have also some hope that indeed we can approximate some semi-classical physics with our lattices if we go to this infinite volume and zero lattice spacing limit. So we wanted to push further into this large kappa 2 direction. However, the acceptance rate of our Monte Carlo algorithm dropped significantly to like 10 to the minus 6 or even below that. So our numerical methods were extremely inefficient in that sense. But in view of time, I will actually skip the part where I tell you what a great algorithm we developed to circumvent that. I will just briefly summarize it. So we
to hear a little bit of it.
Okay. If you're interested in it, then I'm happy to go through it. So previously we used standard metropolis algorithms, and I will just go through it on the level of an Ising model, just 2D Ising model, where what you would do is you pick a lattice site by random, compute the energy contribution, and then if the energy contribution is positive, you flip the spin, and if it's negative, then you toss a random number, and if the random number is larger than the exponential weight of that, then you still flip the spin, and if not, then you don't do anything, and you repeat from 1. And of course, so this becomes very inefficient if this if condition is never satisfied, because then you mostly don't do anything.
You don't have a hybrid algorithms available to you here.
No. It's not yet, at least. So it's really pure Metropolis Hastings that we used. And what we then did, because the main issue that we have is low acceptance rate, we adapted an algorithm known as kinetic Monte Carlo, so a rejection-free algorithm. And here the idea is that you have some overhead, so you initialize, and one implementation is that you say that you create 2 lists. You create a list of all probabilities at each lattice site on where you could flip the spin, and you also create a list of the summed probabilities. So this list here is just the sum of all entries up to the index j. So the first entry is just this value. The second entry is the sum of this plus this. The third is the sum of this plus this plus this, and so on. And then we toss a random number between 0 and the last entry of that list. So the full sum of all probabilities. And then find the lattice site such that the random number is enclosed in two of these entries. So, and for example, here, I set t equals 1 and r equals 3.1. And this means that I pick this lattice site because 3.1 is between 2.44 and 3.4. So I pick this entry here and flip the corresponding spin. And then I update the entries of the probability and the sum of probabilities. There you go. And then I repeat from 2. So I toss a new random number and repeat the whole process again. So with each tossing a random number, I flip a spin by design. And what it does is that this algorithm kind of goes from absolute probabilities in the sense of is a given lattice site likely to flip or not, to relative probabilities, like which lattice site is most likely to be accepted next. And yeah, so this is the standard implementation of it. And one issue that comes with it is that Monte Carlo time or time evolution is typically measured in attempted moves, not accepted moves. So if I had, like, again, think about the Ising model and I have observable, for example, the average magnetization, I can be in a regime where the acceptance rate isn't very high. So I flip a couple of, I attempt a couple of moves, but I never accept any of the moves until eventually I accept a move, and then I accept the opposite move, and so on. So there's some time evolution of this observable with some states that seem to be roughly stable. Now with the new algorithm, I don't have these points where something remains stable, because by design, I removed all ways where the where no move anything where the move any step where the move is not accepted. So one has to map the time dependence of this new algorithm to the standard Metropolis Hastings algorithm. And in the simplest case, which unfortunately doesn't hold for gravity, one can just compute the number of rejected moves corresponding to an accepted move. And this, in a sense, is some form of reweighting of a given accepted move. And this has been done. I mean, this is very common to do it in dynamical systems like growth of crystals and so on. People very commonly do it. For gravity, the case is a little bit more complicated. Mostly, and I will not go into the details here, mostly because the action that we're using has a global part. So as I said, it depends on the total number of 4 simplices and the total number of 2 simplices. And this changes. So the partner moves change the number of 2 simplices and 4 simplices. So in the sense, the entire probability of all moves always changes after any move. And therefore, we would have to update all of these entries all the time, which of course, updating one of these entries means that we have to recompute the probability, which is expensive. So what we did instead was to abandon the notion of Metropolis probabilities and introduce something that we call ponderances, which is, again, something like a relative probability that a move gets accepted. And this does satisfy detailed balance if one takes into account a specific weight that each move gets, again, in the sense of reweighting of a standard of standard Metropolis or Monte Carlo methods. But in that sense, one gives up the notion of a global probability, which is between 0 and 1, and goes to a notion of a specific move is more likely to happen than another move. And we implemented all of this.
Yes. You also have very long autocorrelation times.
This we also have, yes. We also have very long autocorrelation times, and we don't have anything that we don't have anything implemented to beat it. One way to do it would be, for example, parallel tempering. I think this would be rather easy to implement. We haven't done it yet, but we are certainly thinking about it. And yes, autocorrelation is one of the bottlenecks that we have so far, or that we're left with at the moment. Yes. But yeah, so this algorithm it's not like a cluster algorithm on the Ising model where you solve both the acceptance and the autocorrelation issue. It's just solving one of these issues, but yeah, one step at a time. And yeah, to just test that all of these implementations and the generalization of the Metropolis algorithm probability to these ponderances, as we call it, actually makes sense and works. We tested it against the 2D Ising model, and I think what the bottom line that I would like you to take away is that the green line here is the result from from our proposed new method, so the new algorithm. And the black dashed line is a low energy perturbative or low temperature perturbative expansion of the Ising model. And the blue dots are the standard Metropolis results for the for 1 minus the expectation value of the magnetization squared. So we see that the green line very well agrees with both the perturbative computation, analytical computation at low energies, and the Metropolis algorithm at higher temperatures. So that gives us good indication that it actually produces the correct magnetization and works. And we also did a couple of other tests in terms of like the energy distribution, the probability distribution of energy states at a given temperature. But I think the most interestingly, or what the goal was, to improve the performance of the algorithm. And for the Ising model, one can also just think about it and compute it with pen and paper, that the speed up of this rejection-free algorithm compared to the standard metropolis algorithm is just a power law with the acceptance rate. And then we also implemented it for gravity and tested it for gravity, also with some observables that we tested it against to make sure that it produces the same results and so on. And these are the red dots are the performance here. And we see that we do gain some speed up in like 2 orders of the magnitude roughly, but there is a plateau at like small-ish acceptance rate. And we also understand why this plateau, and this is because our lattice becomes more and more connected if we go in this regime. And this means that for a given accepted move, we just have to update more neighbors and again compute more probabilities, so that dampens the speed up. So, but nevertheless, we did gain 2 orders of magnitude in speed up, which I think it's pretty nice. And with this new algorithm, and also by just being a little bit more greedy on computational resources, we were able to explore a couple of more ensembles. So before the rejection-free algorithm, we had roughly 7 ensembles across different, like in the different parameter regions, but also like at different volumes, and 7 out of them were tuned. And now we have explored around 1,300 and 24 out of them are tuned. So for a given lattice spacing or for a given value of kappa 2, we have various volumes at which we have a tuned ensemble. And so this allows us to now, in my opinion, really do a reasonable infinite volume and finite and 0 lattice spacing extrapolation, because we have more data points than just these 7. So one point that I wanted to that maybe makes sense to mention, because you asked about it earlier, and I know that I'm already running over time, so just let me know when I should wrap up. So to like how we now get the relative and absolute lattice spacing. So what the key object here is to look at the so-called Schelling function. So you start at a given simplex, and then you go a specific one hop away and count how many neighbors that has, and then you do that at a given geodesic distance and just count how many neighbors you find. And this would give you some form of volume profile of your geometry. And if the volume, or if the geometry would be a de Sitter sphere, then the volume profile would be something like a cosine cubed. And this is this black line here. And what we actually find on the lattices are more like these green, yellow, and red lines at small-ish values of kappa 2. So here we would say, okay, we have this large asymmetric tail, and this is caused by unphysical features, so-called baby universes, so like branches of the main sphere. And these are undesired features, and we don't want them. But if we go to larger values of kappa 2, which is exactly the way that we are going to, in the hope of finding a continuum an endpoint.
So this kappa 2 was the cosmological constant term, isn't it?
No, kappa 2 was the Newton, like roughly related to the Newton coupling, but it's the Baire coupling. So yeah, but it's kappa 2 was what was related to the Newton coupling. Kappa 4 was the one multiplying the n4, so it's more related to the volume.
That's really hard.
But I mean, in the end, it's just a lattice parameter. But it's a Baire parameter, and how that actually relates to a physical Newton coupling, the one would have to do.
It's related to the curvature of the sphere. I mean, there's a solution to the Euclidean Einstein with the cosmological constant.
Oh yeah. In that sense, in the discretized sense, of course, yes. But it's still like the Baire couplings, and it's not the renormalized one, and so on. So sure. So and also yeah, I think there is also some linear combination and some offset related. So it's not just the Newton coupling, but it's related to the Newton coupling. but yes, it is related to the Newton coupling, and we go to larger values of a bare coupling, which, however, doesn't mean that the actually renormalized Newton coupling becomes larger. I think that's what I would like to emphasize, that kappa 2 going to infinity is not an issue. So it wouldn't mean that the Newton coupling would go to infinity.
What I was trying to get into my head is whether the radius of the sphere is getting larger or smaller. And
so, I mean, so the point is that, so the argument of the point, like, we can only talk about the radius if it is actually a sphere.
Yeah.
And so with these, like the red line, for example, it would be a smallish sphere with many outgrowths on it, which would mean that you have actually like this large distance tail, because like you can go from one outgrow, you would have to go to the big sphere and then move into the next outgrow. So this causes these large asymmetric tail. And this asymmetric tail shrinking means that these outgrowths shrink and that you actually become more spherical, like that your sphere actually becomes more, it actually becomes a sphere in the first place, like it becomes a smoother sphere than it was before. But and therefore, of course, the radius slightly increases because the volume that previously was in the outgrowths now is in the sphere. But this is still, and the question of whether the sphere in physical volumes decreases or shrinks, this depends on the lattice spacing and the total number of four simplices that you have in here. And we try to keep that fixed along these ones, but it's not so easy to keep it fixed. But yeah, so the bottom line is that following along this idea of going to larger values of kappa 2, our geometries actually approximate a sphere better and better. Again, indicating that there might be a de Sitter profile if we go to even larger values of kappa 2, which would mean that these lattice geometries do or would resemble something like a smooth geometry. And now to determine the absolute and relative lattice spacing, as I said, we perform a saddle point approximation on the lattice, and then the expectation value of the number of four simplices in the saddle point approximation is just given by k squared, which is some constant over for kappa 4 minus kappa 4 c, where kappa 4 c is the tuned value of kappa 4. So since n4 is constant because we fix the volume, we can solve this and find a linear relationship between the square root of n4 and the value of kappa 4. So by computing kappa 4 as a function of n4, we can test whether there's this linear relationship. And this also tests us whether we recover this semi-classical limit in the sense of a saddle point approximation. And in addition, I can also look at the same saddle point approximation in the continuum. And there, if one assumes that one is dominated by the Hawking-Moss or the de Sitter instanton, then this is just given by exponential of 3 pi over g times lambda. So here, now I have a relation between our lattice observables and something like the Newton coupling. So we can extract the Newton coupling from our lattice data by comparing it to 1 over this slope here. And this is what allows us to indeed translate our lattice unit into physical units and get some absolute and relative lattice spacing. So one example is here. It's just an example plot where we fix the volume, we fix kappa 2, and then we tune the value of beta, so the second parameter, and at n4 equals 16,000 and kappa 2 equals 2.245. Beta equals minus 0.544 is the tuned ensemble. So this is the one where you think it's closest to the transition, and this corresponds to this plot and to this point here. And then we just go to larger volumes at the same value of kappa 2 and beta, and compute the value of the renormal or the tuned cosmological constant. Of kappa 4, which is related to the cosmological constant. And already pi by I, we see that it's roughly a linear scaling between them, and we can actually extract this slope, which was important to extract the Newton coupling. And we get some statistical and some systematic error, which we get by choosing which of these points we actually do include in the fit. Like we remove this one, for example, and that one to get some systematic uncertainties. And then we do that we extract the slope for all of our ensembles, so for all volumes and tuned ensembles, and compute the value of G, so the finite volume, finite lattice spacing equivalent of a Newton coupling. And at a given lattice spacing, we perform an infinite volume extrapolation of these values with 1/4 and 1/1 volume and 1/1 volume squared correction. And for for one set of lattices, which we call fine lattices, it's just a value of kappa 2. We get that G is 0.477. And since we take that as a reference spacing, we say, okay, this is everything that this is the lattice spacing that we call 1, or this lattice spacing equals 1. This means that we can now relate it to physical units and say, okay, the fine lattice spacing is 1.29 times the Planck length. So it's a little bit above the Planck length. But we also have smaller lattice spacings. So the superfine, for example, it's a different value of kappa 2. We get a different value of G. And this allows us to find a relative lattice spacing between the fine and the superfine lattice spacing. We see that the superfine one is smaller than the fine and around the Planck length. So the lattice spacings decrease for larger values of kappa 2, and we also have one at 4.1, and see again that this trend continues and reach the Planck length in our simulation. So we are really at Planckian lattice spacings in this sense. And this is one example on how a saddle point approximation and a comparison with semi-classical physics in the continuum allows us to translate lattice units into physical units. And there was something more that I wanted to say maybe about cosmology. So we also find indications for potentially having a dark energy component in our system. But I guess in view of time, I might skip that and talk about it if somebody asks specific questions about it. And so I just very briefly summarized that I explained asymptotic safety as quantum realization of scale symmetry. I gave you a very brief upshot on functional methods and an example on how functional methods can be used to constrain quantum gravity by using matter. Then I focused on EDT and advocate that EDT with this non-trivial matter term is a tool to explore asymptotically safe quantum gravity. And we used scalar fields to probe the geometries. So really just using them as an observer field in a sense to see how these how these geometries influence the scalar, and find that they behave, or that the geometries look like 4-dimensional ones, at least to these scalar fields. Then I've briefly highlighted some new algorithmic development, which allows us to efficiently compute larger volumes and finer lattice spacings, and that lattice geometries resemble semi-classical de Sitter space with a Hausdorff dimension of 4. And I skipped the contact with cosmology. And as an outlook, I've already mentioned a few. So we are currently improving parallelization to deal with the high connectivity, and also thinking about parallel tempering to reduce autocorrelations, and study dynamical matter with this new algorithm to really dive into the question on whether also on the lattice these Landau poles of standard model subsectors can be resolved or not. And yes, thank you very much for your attention. And I'm happy to answer more questions.
Thank you very much. Any questions? I had a couple of questions. So one of them is, so at the beginning you mentioned that one of the things to be careful of in these lattice methods is finite size effect. And maybe it showed up a little bit in your de Sitter example, but could you give some examples of maybe some non-trivial effects that have showed up in some calculations that you later realized were finite size effects and go away otherwise?
No, I mean, one just has to be careful in the sense that we like, I guess we didn't run into any issues where we thought, okay, we had something under control, and then later on we find something completely different. But I mean, we are making extrapolations to zero lattice spacings, right? We compute stuff at finite lattice spacings, and then we extrapolate to vanishing lattice spacing. And of course, there we kind of assume that we are already in a linear or quadratic or in a regime where a linear or quadratic deviation from zero lattice spacing is a good approximation. But this, of course, you don't know whether this is the case until you find that it's not. So when it's an assumption. It's something that is very hard to test whether this is a good assumption or not. And I like some anecdote, but I remember the first Lattice conference that I joined a talk where some very senior, I mean not old, but like an established researcher in the field gave a talk on different fermion discretizations in just QCD, standard QCD, on regular lattices, and he actually showed that what people previously assumed, that all of these, if extrapolated to zero lattice spacing, should agree and give exactly the same result. This was not the case, and that one indeed was very far away from this linear scaling that one typically uses for the extrapolation. So in that sense, the systematic errors or uncertainties on the lattice were underestimated in this case, but it's also very hard to estimate what they actually are. But yeah, so I just mentioned it as a caveat that it's an extrapolation, so it's an assumption.
I guess I was a little more curious on the infrared side of things, like if there are any boundary effects or something like that.
Oh yeah, so I mean, the infrared effect is
the topology of your lattices of your system as well. The topology it was using, which I didn't get.
So yeah, so we fixed the topology to be a sphere.
Always a sphere.
Yeah, it's always like in this EDT configuration, it's always a sphere, so it's just S4. And these partner moves are such that the sphere that the topology doesn't change. So we fix the topology as S4, and then we go for it. And CDT typically puts it on a torus, so S3 cross I1, and then they identify the time slices, so they have a toroidal topology, and this also remains fixed because partner moves preserve the topology. Regarding infrared effects, so this is like the infinite volume extrapolation. This is what gives us what removes the finite volume effects. And let me see if I have a nice plot where one sees that this is kind of necessary. Yeah, so I mean, like here we plot some quantities as a function of 1 over the volume, and then you still have to check whether. So here we needed a quadratic contribution to the volume dependence to properly fit these data points. So in that sense, there's always a competition of adding more terms to your fit. But yeah, so this is a fit to the plane. So we fit both. We make an extrapolation, a simultaneous extrapolation in the lattice spacing A and in 1 over the volume. And you see that there's some non-trivial dependence on the volume here. So this finite size, finite volume effects are important. I think especially here we also are underestimating a little bit these effects, because I mean we're talking about a bound state, a gravitational bound state of two particles. So this, in a sense, is already a somewhat non-local notion, and on the small volumes that we have, it's one. Yeah, I guess one might want to be careful with what the extent of such a bound state would be, and whether it actually can be confined on such small volumes. So certainly, it's worth revisiting this with larger volumes and finer lattice spacings, and seeing whether this trend continues, and whether one can pinpoint the error bars to smaller values, or whether one sees indeed that this was just finite size effects. Yes.
The quadratic dependence there is very weak. I think a line would be within the error bars as well.
Yes. Yeah. I guess yes. We did play around with obviously different fit functions, and for some of these like lattice spacings, a line would have been perfectly fine. I think we did pick a 1 over volume squared.
I'm sure you had your reasons.
Yeah, I mean, we played around with different fit functions and chose the one that gave like the most statistically relevant one.
I also wanted to ask a little bit about your dynamical dark energy. I know you didn't have time to say anything about it, but just qualitatively, I was wondering, is it a monotonically decreasing dark energy? Is the sign fixed? Just some general
Okay, so
aspects of it.
maybe as a caveat, so I'm not a cosmologist, so for me, what we did was to so the short point is that we focus on these volume profiles, because this is, I mean, it's the shape of the universe, so it's the shape of the volume, so we can connect that with somehow with cosmology, and we use like Friedmann equations in Euclidean vacuum space. So this is pure gravity, no matter. And this depends on A and A dot, and it's given by lambda over 3, which would be the actual cosmological constant. And we can extract, or one can identify A, the scale factor, as the third root of this Schelling function. So that I guess there's arguments that well, it's basically like the radius of it, or somewhat related to the radius of that Schelling function, because the Schelling function is the 3D volume of your universe at a given Euclidean time tau. So the scale factor is with some prefactor the third root of it, and we can compute that. So we can compute the left-hand side of the Friedmann equation from the lattice, and this gives us some, like the right-hand side, which would be a cosmological constant. But what we observe on the lattice is that this is indeed not a constant, but that there is some dependence on this on our lattice ensembles, and we said, okay, let's approximate this by a constant plus a function of the Hubble rate A dot over A. And then in particular, we used a specific model by João Solar to assume that lambda is a constant plus an h squared correction plus an h dot correction, and then fitted or tried to extract these parameters nu and nu tilde from our lattice data, and try to fit these parameters. And what we find is that in this model, nu tilde is very close to 0, and nu is of the order of 10 to the minus 3. And so this particular model, in particular that nu tilde is 0, is a vacuum energy model which covariantly conserves the vacuum energy. independent of a matter content. It avoids experimental constraints because it's small enough. In principle, it could lead to modifications of the power spectrum, but it's like because nu is so small, it's not distinguishable from lambda CDN. But again, so typically, I think also this specific model, or typically these dark energy models, require some form of matter field to give the dynamics. And here, this is just pure gravity. So yeah, I think at least for me, there's still a couple of questions on how to really match it to cosmological models, and how one could maybe make a more model independent notion on dynamical dark energy. Because here we just, I mean, we used a very specific model and showed that in this model, one of these parameters is significantly statistically significantly away from zero.
You also have the problem that you're in Euclidean time.
Yes, we also have the problem that it's Euclidean time and that we are not really in a Lorentzian universe, and how to rotate our results back to Lorentzian times, I don't know. But I mean, even if I were to go to CDT, this question would remain. So I like once you employ Monte Carlo methods in that sense, it's, at least for me, very unclear how I would ever be able to go back to Lorentzian spacetimes. Yes.
And lambda naught is put in by hand.
Sorry?
Lambda naught, is it?
Lambda naught is also a fit parameter. I mean, we can, yeah, we like, this is just, I mean, so we fit lambda as a constant plus 3 nu times h squared. Right. So
I think effectively lambda naught is an input parameter because it's probably related to kappa 2 and kappa 4.
Yes. Effectively, it will be related to kappa 4, but here we leave it as a fit parameter.
Okay.
Still.
And so does it match the present day value?
Well, it's still in lattice units, so I guess that's a good question. I haven't thought about relating the lattice cosmological constant in like real cosmological constant, but yeah, I will think about it. I haven't how one would do that. It should be possible because we have a relation of lattice units into physical units. So yeah, I think about it. That's a good point.
Thanks. Any other questions?
Just in with regard to your algorithms, have you tried normalizing flow? These neural network type of tricks. Your system looks like it's rather suited to something along those lines.
Yeah, we haven't tried it. At least in this sense, we haven't tried it. I have thought about it, and like, yeah, it should. I mean, it should be this like trivializing maps should. I mean, there should be a straightforward application here. The question is, of course, always like how many configurations do you need to train your data properly, and how many do you even need to get reasonable statistics out of whatever observables you want. So I guess, but I think that's true in any of these applications. There's always a trade-off between how much training data do you need and how much statistics do you in the end need for your observables. But yeah, we haven't done it. I thought about it, but yes, it's certainly something on the technical side of the lists. Yes.
So I should stop the recording and we can. Thanks.
Mhm.